There are moments in history when a single image changes everything. When the photograph known as Photo 51 was captured in May 1952, few could have imagined that this seemingly abstract X-ray diffraction image would help unlock the secret of life itself. The person behind the camera, or more accurately, behind the complex X-ray crystallography equipment that produced this landmark image, was not a celebrated scientific figure. She was a meticulous, brilliant British scientist working in a small, damp laboratory in post-war London. Her name was Rosalind Franklin. Today, most people recognize the names James Watson and Francis Crick as the discoverers of DNA's double helix structure, an achievement that earned them the Nobel Prize in 1962, along with Maurice Wilkins. Their discovery revolutionized our understanding of genetics and laid the groundwork for countless advances in medicine, biology, and biotechnology. But the story that's been told for decades, the story that appears in most textbooks, omits a crucial chapter. It fails to acknowledge the woman whose experimental work was essential to this discovery, whose data was used without her knowledge or permission, and whose contributions were diminished, dismissed, and nearly erased from scientific history. This is the story of Rosalind Franklin, the forgotten pioneer of molecular biology, whose work was instrumental in one of the greatest scientific breakthroughs of the 20th century. It's a story about brilliant science, about perseverance in the face of institutional sexism, and about how history is written, and by whom. Join us as we explore the life and legacy of a woman who changed our understanding of life itself, only to be written out of the narrative she helped create. Rosalind Elsie Franklin was born on July 25, 1920, in Notting Hill, London, into a prominent Anglo-Jewish family. Her father, Ellis Franklin, was a banker, and her mother, Muriel Whaley, came from an equally distinguished family. The Franklins were well-established, wealthy, and placed high value on education, public service, and social justice. From an early age, Rosalind showed remarkable intellectual abilities. By the time she was 6, she knew she wanted to be a scientist. This wasn't just a passing childhood fancy. It was a calling that she pursued with the determination and focus that would characterize her entire life. "Science," she would later write, "and everyday life cannot and should not be separated." Rosalind attended St. Paul's Girls' School, one of the few educational institutions in Britain at that time that emphasized science education for girls. There, she excelled in physics, chemistry, and mathematics. Her scientific aptitude was so evident that at age 15, she had already decided to pursue a career in chemistry. In 1938, at the age of 18, Franklin gained admission to Newnham College, Cambridge, one of the 2 women's colleges at the University of Cambridge. This was a significant achievement at a time when few women pursued higher education, especially in the sciences. At Cambridge, she studied physical chemistry under the supervision of Ronald Norrish, who would later receive the Nobel Prize in chemistry. Despite the prestige of attending Cambridge, Franklin's experience there revealed the gender disparities that would shadow her throughout her career. Cambridge didn't actually grant degrees to women until 1948, 7 years after Franklin completed her studies. She received only a degree titular, not the full Bachelor of Arts degree that her male counterparts received for the same academic achievement. After completing her studies at Cambridge in 1941, Franklin briefly worked as a research assistant. But World War II was raging, and she soon took a position with the British Coal Utilization Research Association, CURA, where she applied her skills in physical chemistry to study the porosity of coal. This research had practical wartime applications for gas masks and would form the basis of her doctoral thesis. In 1945, Franklin earned her PhD from Cambridge University with a dissertation titled The Physical Chemistry of Solid Organic Colloids, with special reference to coal. Her research on the microstructures of coals and carbons was so thorough and advanced that it remains relevant in coal science to this day. Following the war, Franklin sought to expand her scientific horizons. She secured a position in Paris at the Laboratoire Central des Services Chimiques de l'État, where she worked from 1947 to 1950 under the guidance of Jacques Mering, a renowned X-ray crystallographer. It was here that Franklin mastered the techniques of X-ray crystallography, the very methods she would later apply to DNA with such precision. The time in Paris would prove to be one of the happiest and most productive periods of Franklin's life. The French scientific community was more egalitarian than Britain's, and Franklin thrived in an environment where she was valued for her intellectual contributions rather than being marginalized because of her gender. She developed lifelong friendships and published several important papers on the structure of carbons that established her reputation as a skilled researcher. In later years, she would look back fondly on her time in France, where she had been treated as a scientist first and a woman second, a stark contrast to what awaited her upon her return to England. In 1950, Rosalind Franklin returned to London to accept a position at King's College London, where she had been recruited by the lab director John Randall. Franklin was hired specifically to apply her expertise in X-ray crystallography to the study of DNA, deoxyribonucleic acid. At the time, DNA was known to carry genetic information, but its structure, how it was actually organized at the molecular level, remained a mystery. Understanding this structure would be the key to understanding how genetic information is stored and transmitted. Franklin arrived at King's with the expectation that she would be leading her own research project on DNA structure using X-ray diffraction techniques. However, from the very beginning, her position at King's was compromised by poor communication and gender politics. Before Franklin's arrival, Maurice Wilkins had been working on DNA at King's. While Wilkins was away on holiday, Randall wrote to Franklin stating that she would take over the DNA work, with only technical assistance from Wilkins. This crucial information was never clearly communicated to Wilkins, setting the stage for a misunderstanding that would have profound consequences. When Franklin arrived, Wilkins assumed she was hired to be his assistant, rather than a peer researcher with her own project. This miscommunication immediately created tension between the two scientists, a situation exacerbated by their contrasting personalities and working styles. Franklin was direct, exacting, and unwilling to speculate beyond what her data explicitly showed. Wilkins was more reserved and found Franklin's assertiveness off-putting. Their relationship quickly deteriorated into one of mutual distrust and minimal communication. The environment at King's College further complicated matters. King's was a traditional institution with distinctly separate spheres for men and women. The main dining room, where scientific discussions often continued over meals, was for men only. Female scientists had to eat elsewhere. Even the coffee room was male-dominated territory where Franklin rarely felt welcome. Despite these challenges, Franklin set up her laboratory and began her work on DNA with graduate student Raymond Gosling. She approached the problem with methodical rigor, improving the X-ray diffraction techniques to obtain clearer images than had previously been possible. By the end of 1952, after 2 years of painstaking work, Franklin had made several crucial discoveries. First, she identified that DNA existed in 2 forms, a dry A form and a wet B form, with a different structure. This insight was vital because previous researchers had obtained confusing results by not recognizing they were looking at 2 different forms of the molecule. Second, she discovered that in the B form, which is the form DNA takes in living cells, the molecule has its phosphate groups on the outside. This contradicted prevailing theories and provided a key insight into DNA's structure. Third, she determined that the B form had a helical structure, with 2 repeating units per helical turn. Her calculations on the density of DNA also indicated that the molecule had to contain 2 strands, not 1 or 3 as some had proposed. Most significantly, on May 6, 1952, Franklin and Gosling captured Photo 51, an exceptionally clear X-ray diffraction image of the B form of DNA that clearly showed its helical nature with a distinctive X pattern. Franklin was cautious and thorough in her approach to science. She wanted to gather comprehensive data before publishing definitive conclusions about DNA structure. By January 1953, she had drafted a manuscript that correctly described many features of the DNA double helix, including its helical nature and the location of the phosphate groups. She was getting very close to solving the full structure. But events were unfolding elsewhere that would forever alter the narrative of DNA's discovery and Franklin's place in it. While Rosalind Franklin was methodically gathering data at King's College, a parallel effort to determine DNA's structure was underway at Cambridge University's Cavendish Laboratory. There, American biologist James Watson and British physicist Francis Crick were taking a different approach to the problem. Unlike Franklin, who was generating original experimental data through X-ray crystallography, Watson and Crick were building theoretical models based primarily on data generated by others. They were trying to construct a three-dimensional model of DNA that would explain all its known properties and behaviors. The race to discover DNA's structure was competitive, but not unusual in the collaborative, competitive world of science. What was unusual and ethically problematic was how Franklin's data made its way to Watson and Crick without her knowledge or consent. The crucial transfer of information happened through multiple channels. In January 1953, Maurice Wilkins showed James Watson Photo 51, Franklin's clear X-ray diffraction image showing the helical structure of DNA, without Franklin's knowledge or permission. Watson later described his reaction to seeing the photo in dramatic terms. "The instant I saw the picture, my mouth fell open and my pulse began to race." Additionally, Max Perutz, a scientist at the Cavendish Laboratory, had received a report from a committee that was evaluating the work at King's College. This report contained Franklin's unpublished data and conclusions about DNA structure. Perutz shared this information with Watson and Crick, again without informing Franklin. Armed with Franklin's crystallographic data, which they couldn't have generated themselves, and her insights about the molecule's dimensions and water content, Watson and Crick had the missing pieces they needed. Within weeks, they built a model of DNA as a double helix with the specific structural details that Franklin had been carefully documenting. On February 28, 1953, Watson and Crick reached their breakthrough, completing the model of the DNA double helix. Francis Crick famously announced at the local pub, the Eagle in Cambridge, that they had discovered the secret of life. The race concluded with 3 papers published consecutively in the April 25, 1953 issue of Nature. The first was by Watson and Crick, proposing their model of DNA as a double helix. The second was by Wilkins and colleagues, providing supporting evidence. The third was by Franklin and Gosling, presenting their X-ray diffraction data, including the critical Photo 51, but not directly interpreting it in terms of a double helical structure. The sequencing of these papers created the impression that Watson and Crick's theoretical work had come first, with Franklin's experimental data serving merely as confirmation. In reality, the chronology was reversed. Franklin's experimental work had preceded and enabled Watson and Crick's model building. In their paper, Watson and Crick included only a vague acknowledgement of having been stimulated by a knowledge of the general nature of the unpublished experimental results and ideas of Dr. M.H.F. Wilkins, Dr. R.E. Franklin, and their co-workers at King's College London. This minimal acknowledgement obscured the extent to which their model relied on Franklin's data. It was a crucial omission that would shape how the discovery was perceived for decades to come. By the time the papers were published, Franklin had already decided to leave King's College. The tension with Wilkins, the inhospitable environment for women scientists, and the opportunity for a fresh start led her to accept a position at Birkbeck College, London, where she would apply her expertise to the study of viruses. The race for the double helix was over. Watson and Crick had won, and history was already being written in a way that would minimize Franklin's contributions. After leaving King's College in March 1953, Rosalind Franklin began a new chapter at Birkbeck College, joining the research group led by crystallographer J.D. Bernal. Bernal was known for his progressive politics and for fostering an inclusive laboratory environment, a stark contrast to the atmosphere Franklin had endured at King's. At Birkbeck, Franklin shifted her focus from DNA to the study of viruses, particularly tobacco mosaic virus, TMV. This was not a step down or away from important science. Rather, it was the beginning of what many colleagues later described as her most productive and innovative research period. Franklin approached virus research with the same meticulous attention to detail and technical innovation that had characterized her DNA work. She improved X-ray crystallography techniques for studying viral structures and quickly established herself as a leader in the emerging field of structural virology. Between 1953 and 1958, Franklin published 17 papers on viruses, each representing significant advances in understanding their molecular structure. Her work on TMV was particularly groundbreaking. She determined that the RNA in the virus was wound in a helical fashion and embedded in the protein rather than in a central hollow cavity, as previously thought. By 1956, her research group had made such significant progress that the U.S. National Institutes of Health awarded them a grant to study the structure of the polio virus. Franklin was even invited to build a model of TMV for the 1958 Brussels World's Fair exhibition, a public acknowledgement of her growing scientific reputation. During this period, Franklin also found greater personal fulfillment. At Birkbeck, she mentored younger scientists and built collaborative relationships that had been difficult to establish at King's. She developed close friendships, traveled extensively across Europe and the United States, and enjoyed hiking trips, showing a side of her personality that contradicted the stern image sometimes depicted by those who had known her only at King's. Franklin's former PhD student, Aaron Klug, who would later win the Nobel Prize in Chemistry in 1982, described her as generous and supportive. She treated me as an equal, not as a technical assistant, which I was supposed to be. Klug would continue Franklin's work on virus structures after her death. Despite her scientific productivity and growing recognition, Franklin's health began to deteriorate in mid-1956. She developed symptoms that were eventually diagnosed as ovarian cancer. The illness may have been related to her extensive exposure to X-rays during her career, a connection that adds another layer of tragedy to her story, suggesting that the very tools that enabled her scientific breakthroughs may have contributed to her illness. With characteristic determination, Franklin continued working throughout her illness, even during periods of treatment. She maintained her laboratory activities until just a few weeks before her death, demonstrating remarkable resilience and dedication to her research. Rosalind Franklin died on April 16, 1958, at the age of 37, leaving behind a significant body of work that extended well beyond her contributions to DNA structure. Her death came 4 years before Watson, Crick, and Wilkins received the Nobel Prize for the discovery of DNA's structure. The Nobel Prize is not awarded posthumously, so Franklin could not have been included in the 1962 award, even if the Nobel Committee had wanted to recognize her contributions. However, the question remains whether she would have been included had she lived, a question that encompasses issues of scientific credit, gender bias, and how discoveries are attributed in competitive, collaborative fields. On October 18, 1962, the Nobel Committee announced that the Nobel Prize in Physiology or Medicine would be awarded jointly to Francis Crick, James Watson, and Maurice Wilkins for their discoveries concerning the molecular structure of nucleic acids and its significance for information transfer in living material. Rosalind Franklin had been dead for over 4 years. The Nobel Prize statutes do not allow for posthumous awards, so Franklin could not have been included regardless of the committee's assessment of her contributions. This timing has sometimes been used to dismiss questions about whether Franklin received appropriate credit, but the issue runs deeper than Nobel recognition. The more significant question is how Franklin's role in the discovery was characterized in the subsequent historical narrative, and how that characterization reflects broader patterns of marginalizing women's contributions to science. In 1968, James Watson published The Double Helix, his personal account of the discovery. The book became a bestseller and shaped the public's understanding of how DNA's structure was determined. In it, Watson portrayed Franklin in unflattering terms, referring to her as Rosie, a nickname she never used, criticizing her appearance and dress, and depicting her as difficult, emotionally volatile, and unwilling to collaborate. Watson wrote that Franklin had to go or be put in her place, and described her as belligerent and unable to interpret her own data. He characterized her as an obstacle to progress rather than a key contributor to the discovery. This portrayal, coming from one of the most celebrated scientists of the era and presented as the authoritative account of the discovery, did immense damage to Franklin's scientific legacy. It reinforced stereotypes about women in science and obscured Franklin's technical expertise and the quality of her experimental work. Watson's account went largely unchallenged for years. Franklin was not alive to defend herself, and many who knew her were reluctant to engage in public controversy. As a result, generations of students learned about DNA's discovery through Watson's lens, with Franklin cast as a minor character at best, an impediment at worst. The historical erasure of Franklin's contributions exemplifies what science historian Margaret Rossiter has termed the Matilda effect, the systematic under-recognition of women scientists, and the attribution of their work to male colleagues. This pattern has affected countless women throughout the history of science, from Lise Meitner in nuclear physics to Jocelyn Bell Burnell in astronomy. In Franklin's case, several factors contributed to this erasure. First, the cultural context of 1950s Britain placed significant barriers before women in science. Women were expected to serve as assistants rather than lead researchers, and assertive women who demanded professional respect were often labeled as difficult or uncooperative. Second, the collaborative competitive nature of scientific discovery makes attribution complicated. Science progresses through the exchange of ideas and data, but when this exchange happens without proper acknowledgement, as when Franklin's data was shared without her consent, the resulting credit allocation becomes distorted. Third, the storytelling around scientific discoveries tends to favor simplicity over complexity. The narrative of two brilliant young scientists, Watson and Crick, having a eureka moment makes for a better story than the messy reality of incremental progress involving multiple researchers. Fourth, Franklin's early death meant she could not advocate for her own place in history or continue to build her scientific reputation in ways that might have forced a reassessment of her earlier work. The historical record shows that Franklin's data was essential to the discovery of DNA's structure, that her interpretations were largely correct, and that her scientific approach was methodologically sound. Yet for decades, her contributions were minimized, while Watson and Crick were elevated to the status of lone geniuses who solved one of science's greatest mysteries. This pattern of erasure has consequences beyond historical accuracy. When women's contributions to science are systematically under-recognized, it reinforces the misconception that women are less capable of scientific achievement. It deprives young women of role models and perpetuates barriers to inclusion in scientific fields. The story of how Rosalind Franklin was written out of history is not just about one woman or one discovery. It's about how science remembers its pioneers and whose work is deemed worthy of remembering. For years after her death, Rosalind Franklin remained largely unknown outside specialized scientific circles. Her contributions to unraveling DNA's structure were mentioned briefly in textbooks, if at all, The prevailing narrative centered on Watson and Crick as the sole heroes of the discovery. The process of correcting this historical oversight began slowly. In 1975, science historian Anne Sayre, who had been a friend of Franklin's, published Rosalind Franklin and DNA. Sayre's book challenged Watson's characterization of Franklin and detailed the extent to which Watson and Crick had relied on her unpublished data. It was the first significant effort to reclaim Franklin's place in scientific history. However, Sayre's book received limited attention at the time, and the process of re-evaluating Franklin's role gained meaningful momentum only in the 1990s and early 2000s, coinciding with broader efforts to recognize women's contributions to science. Several factors contributed to Franklin's gradual restoration to the DNA discovery narrative. First, the feminist movement in academia led to increased scrutiny of how women scientists had been represented in historical accounts. Scholars began to systematically examine cases where women's contributions had been minimized or erased, with Franklin becoming a prominent example. Second, surviving scientists who had known Franklin, including Aaron Clogue and Raymond Gosling, began speaking more publicly about her skills and contributions. Their first-hand accounts contradicted the unflattering portrayal that had dominated the narrative for decades. Third, the release of previously private correspondence and laboratory notebooks provided documentary evidence of Franklin's insights and the chronology of the discovery, showing how close she had come to determining the structure independently. A watershed moment came in 2002 with the publication of Brenda Maddox's comprehensive biography, Rosalind Franklin, The Dark Lady of DNA. Unlike earlier accounts, Maddox's book received widespread attention and helped bring Franklin's story to a broader audience. The biography portrayed Franklin as a complete person, not just a scientist, but a complex individual with varied interests and relationships, and meticulously documented her scientific achievements. The same year, the British Broadcasting Corporation, BBC, produced a documentary titled Secret of Photo 51, which further raised public awareness of Franklin's role in the DNA discovery. The documentary presented compelling evidence that without Franklin's crystallography work, Watson and Crick could not have built their correct model of DNA. Institutional recognition began to follow. King's College London, where Franklin had conducted her DNA research under difficult circumstances, established the Franklin Wilkins Building in 2000, acknowledging her contributions alongside those of her former colleague. Numerous schools, laboratories, and research institutes have since been named in her honor. In 2004, the Chicago Medical School was renamed the Rosalind Franklin University of Medicine and Science, making it one of the few medical schools in the United States named after a female scientist. The university has established an archive of Franklin's papers and promotes her legacy through educational programs. Perhaps most significantly, in 2015, the UK's Engineering and Physical Sciences Research Council established the Rosalind Franklin Institute, a national research institute dedicated to transforming life science through interdisciplinary research and technology development. The European Space Agency named its Mars rover Rosalind Franklin, scheduled for a future mission to search for signs of past life on Mars, a fitting tribute to a scientist whose work helped unravel the structure of life on Earth. Today, Franklin is increasingly included in scientific textbooks and histories of molecular biology. Her image has appeared on plaques, stamps, and murals celebrating pioneering scientists. Popular culture has also begun to incorporate her story, with plays, novels, and films depicting her life and work. Yet this recognition remains incomplete and still evolving. Many general histories of science continue to mention Franklin only briefly, if at all. The narrative of Watson and Crick as the sole discoverers of DNA's structure persists in popular understanding. Moreover, the recognition that has come is largely posthumous. Franklin herself never experienced the acknowledgement her work deserved. She did not live to see her contributions validated or her scientific reputation fully established. The ongoing process of recovering Franklin's legacy raises important questions about scientific credit, about whose contributions get recognized and whose are overlooked, and about the mechanisms through which scientific history is written and revised. Rosalind Franklin's experience exemplifies what science historian Margaret Rossiter termed the Matilda effect, named after 19th-century women's rights activist Matilda Jocelyn Gage, who first observed the pattern. The Matilda effect describes the systematic under-recognition of women's contributions to science and the attribution of their work to male colleagues. This phenomenon has affected countless women throughout the history of science, creating a distorted record that has profound implications for how we understand scientific progress and who we recognize as capable of scientific achievement. Franklin stands among numerous women whose critical contributions were marginalized, minimized, or attributed to men. Lisa Meitner's experimental work was crucial to the discovery of nuclear fission, yet her research partner Otto Hahn alone received the Nobel Prize in Chemistry for the discovery in 1944. Meitner, who had fled Nazi Germany because of her Jewish heritage, was not included in the award, despite having collaborated with Hahn for 30 years and having provided the theoretical explanation for their experimental findings. Jocelyn Bell Burnell discovered pulsars as a graduate student in 1967, but it was her supervisor, Antony Hewish, who received the Nobel Prize in Physics for the discovery in 1974. Bell Burnell herself has been gracious about the omission, but many in the scientific community view it as one of the Nobel Committee's most significant oversights. Nettie Stevens discovered sex chromosomes in 1905, determining that an organism's sex is determined by chromosomes, the X and Y chromosomes. Despite this groundbreaking work, Thomas Hunt Morgan is often credited with the discovery, and Stevens remains relatively unknown. Chien-Shiung Wu designed and carried out experiments that disproved the law of conservation of parity, a fundamental principle in physics that had been assumed to be unbreakable. Her male colleagues, Tsung-Dao Lee and Chen-Ning Yang, who had theorized that the law might be violated but couldn't prove it experimentally, received the Nobel Prize in Physics in 1957. Wu, whose experimental work was essential to confirming their theory, was not included. Esther Lederberg discovered bacterial genetic recombination and developed techniques that became fundamental to molecular biology, including the replica plating technique still used today. Yet her husband, Joshua Lederberg, received the Nobel Prize in 1958 for their joint work, while Esther's contributions went unrecognized by the Nobel Committee. These patterns of erasure and under-recognition are not coincidental, but reflect deep-seated biases in how scientific achievement is evaluated and credited. Several mechanisms contribute to this systematic marginalization. The Matthew effect, described by sociologist Robert K. Merton, observes that credit for scientific discoveries tends to accumulate to already famous scientists, regardless of who actually did the work. When applied along gender lines, this means that established male scientists often receive credit for discoveries made by less established women researchers. Implicit bias affects how we evaluate scientific competence and achievement. Studies have shown that identical work is rated more highly when attributed to a man than when attributed to a woman. These biases influence hiring, promotion, and recognition decisions throughout scientific careers. Structural barriers have historically limited women's access to scientific education, resources, and positions. When women do make discoveries despite these barriers, their achievements are often seen as anomalous rather than representative of women's capabilities. The leaky pipeline phenomenon pushes women out of science at every career stage, making it less likely that they will reach positions where they can receive proper recognition for their work or advocate effectively for their place in scientific history. Storytelling norms in science favor narratives about individual, usually male, geniuses making breakthroughs in moments of inspiration, rather than the collaborative, incremental nature of most scientific progress. These narratives tend to center male scientists while relegating women to supporting roles. The consequences of these patterns extend beyond questions of individual recognition. When women's contributions to science are systematically erased from the historical record, it perpetuates the false impression that women are less capable of scientific achievement or less suited to scientific careers. This creates a self-reinforcing cycle. Fewer women in science leads to fewer female role models, which leads to fewer girls and women pursuing scientific careers, which leads to continued male dominance in scientific fields and continued marginalization of women who do succeed. Breaking this cycle requires not just identifying and celebrating individual women, scientists who have been overlooked, but addressing the structural and cultural factors that continue to obscure women's contributions to science. The ongoing recovery of Rosalind Franklin's legacy is part of a broader effort to correct the historical record and create a more accurate and inclusive narrative of scientific progress, one that recognizes achievement regardless of gender, race, or other factors unrelated to scientific merit. While Rosalind Franklin's work on DNA structure has received the most attention, particularly in discussions of scientific credit and recognition, it represents only part of her scientific legacy. Her research career, though tragically cut short at age 37, encompassed significant contributions across multiple fields. Before turning to biological molecules, Franklin established herself as an expert on the physical chemistry of carbon compounds. Her PhD work on the porosity of coal was not only academically significant, but had practical applications during World War II, improving the efficiency of coal use as an energy source and enhancing the effectiveness of gas masks. Her coal research revealed her exceptional ability to apply X-ray crystallography techniques to complex, non-crystalline materials, a challenge that required both technical innovation and theoretical insight. This early work established methods that would later prove valuable in her biological research. After departing King's College following the DNA controversy, Franklin pivoted to studying viruses at Birkbeck College. This research phase, from 1953 until her death in 1958, is considered by many colleagues to have been her most productive and innovative period. At Birkbeck, Franklin applied X-ray crystallography techniques to determine the structure of tobacco mosaic virus, TMV, a plant virus that had been studied for decades, but whose molecular architecture remained mysterious. This work required her to develop new approaches to crystallography, as viruses presented different challenges than the DNA fibers she had previously studied. Franklin's virus research yielded several major discoveries. She determined that TMV's RNA, ribonucleic acid, similar to DNA, was located on the inside of the virus particle rather than the outside, correcting previous misconceptions. She established that the virus had a helical structure with protein subunits arranged around an RNA core, findings that provided crucial insights into how viruses are assembled and how they function. She calculated the precise dimensions of the virus particle and the arrangement of its components, creating a detailed structural model that explained how this relatively simple virus could function as an infectious agent. Her TMV work laid foundations for structural virology, a field that continues to be vital in understanding viral diseases and developing treatments and vaccines. The techniques she pioneered for studying viral structures remain relevant in modern research, including recent work on viruses like HIV, influenza, and coronaviruses. Had Franklin lived longer, she likely would have made equally significant contributions to poliovirus research. She had secured funding to study polio just before her final illness, and her preliminary work was continued by her colleagues after her death. Beyond her specific scientific findings, Franklin's legacy includes methodological innovations and a distinctive approach to scientific problems. She was known for exceptional experimental rigor, technical precision, and a refusal to speculate beyond what her data directly supported. This methodological caution sometimes put her at odds with contemporaries who were more willing to make theoretical leaps, but it also ensured that her published findings were robust and reliable. Franklin also played an important role as a mentor to younger scientists. Aaron Klug, who would go on to win the 1982 Nobel Prize in Chemistry for his work on the structure of viruses, was directly mentored by Franklin and continued her research program after her death. Klug has explicitly credited Franklin with shaping his scientific approach and setting him on the path that led to his Nobel-recognized work. In evaluating Franklin's scientific legacy, it's important to consider not only what she accomplished, but what she might have achieved had she lived longer. By her mid-30s, she had already made fundamental contributions to 3 distinct fields: the physical chemistry of carbons, the structure of DNA, and the architecture of viruses. Had she enjoyed a full scientific career, it seems likely that her contributions would have extended even further. The breadth and depth of Franklin's scientific work challenged the narrow framing that reduces her to merely the woman who took photo 51. She was, in reality, a versatile and innovative scientist whose contributions extended well beyond the DNA story that has come to dominate discussions of her career. Much of the narrative surrounding Rosalind Franklin has focused on her professional marginalization and the DNA controversy. While these aspects of her story are important, they can sometimes obscure the fuller picture of who she was as a person and as a scientist. The real Rosalind Franklin was more complex and multidimensional than the caricature sometimes presented in simplified accounts. Colleagues and friends who knew her well described a woman of remarkable intellect, determination, and personal warmth, qualities that don't always come through in discussions focused narrowly on the DNA controversy. Franklin was indeed demanding in her professional standards, both of herself and of others. She had little patience for sloppy thinking or imprecise work, and she could be direct in her critiques. These traits, which might have been admired in a male scientist, were sometimes held against her in the gender-biased environment of 1950s British science. But those who worked closely with her, particularly at Birkbeck College, described a supportive mentor and colleague. Aaron Klug recalled her as a very warm person who was generous with her time and ideas. Raymond Gosling, her student at King's College, later said, "I regarded her as my academic mother. She taught me everything." Beyond the laboratory, Franklin had varied interests and a rich personal life. She was an accomplished mountaineer who loved hiking in the Alps and took challenging climbing trips whenever her schedule allowed. These expeditions revealed her physical courage and her love of natural beauty, aspects of her personality that contrast with the laboratory-bound image often presented. Franklin was also deeply committed to social justice. She came from a family with a tradition of public service, and she maintained a strong sense of social responsibility throughout her life. During World War II, she volunteered as an air raid warden while conducting her coal research. Later, she was concerned about the implications of nuclear weapons and the ethical dimensions of scientific advancement. Her Jewish identity was another important aspect of her life, though not in a religious sense. Franklin was secular in her personal beliefs, but maintained strong connections to Jewish cultural traditions and was deeply concerned about the rise of anti-Semitism in Europe during her lifetime. After World War II, she traveled to Germany as part of her scientific work, but found it difficult to reconcile herself to a country that had so recently perpetrated the Holocaust. Franklin's letters reveal a person with strong familial bonds. She maintained close relationships with her parents and siblings throughout her life, often writing detailed accounts of her research and travels. These letters show her sense of humor, her passion for her work, and her thoughtful observations about the world around her. Franklin was a gifted writer and communicator when addressing audiences interested in her scientific work. Her scientific papers are models of clarity and precision. She took great care in preparing images and diagrams to accompany her publications, recognizing the importance of visual presentation in communicating complex structural information. During her illness, Franklin displayed remarkable courage and determination. Despite undergoing difficult treatments for ovarian cancer, she continued her scientific work almost until the end of her life. She refused to let colleagues treat her differently because of her diagnosis and maintained her focus on completing important research projects. Perhaps most tellingly, when Franklin knew her condition was terminal, she made arrangements for her research to continue after her death. She carefully documented her findings, organized her data, and ensured that her students and colleagues could carry forward the work she had begun. This final act of scientific integrity demonstrates her dedication to knowledge advancement above personal recognition. The real Rosalind Franklin was neither the difficult caricature portrayed in some accounts, nor a perfect martyr to sexism in science. She was a brilliant, complex human being who pursued scientific truth with exceptional rigor and integrity. She had strengths and weaknesses, moments of frustration and triumph, personal struggles and professional achievements, the full range of human experience condensed into a life cut tragically short. Understanding Franklin as a complete person, rather than as a symbol, enhances rather than diminishes her scientific legacy. Her achievements are all the more remarkable when we recognize the full humanity behind them. To fully appreciate Rosalind Franklin's contributions, it's essential to understand the sophisticated technique at the heart of her work: X-ray crystallography. This powerful method allows scientists to determine the three-dimensional structure of molecules at the atomic level, something impossible to observe directly, even with the most powerful microscopes. X-ray crystallography was developed in the early 20th century, with the first structures of simple salts determined by William and Lawrence Bragg in 1913. However, applying this technique to complex biological molecules like DNA represented a formidable challenge that required both technical mastery and innovative approaches. The basic principle of X-ray crystallography relies on the way X-rays interact with atoms in a crystalline sample. When an X-ray beam passes through a crystal, the regular arrangement of atoms causes the X-rays to diffract, scatter, in specific patterns. By analyzing these diffraction patterns, which appear as spots or reflections on a detector, scientists can work backward to determine the arrangement of atoms that produce them. The process is mathematically complex and requires multiple steps. First, the substance being studied must be crystallized, a difficult process for biological molecules like DNA, which tend to form imperfect crystals or fibers rather than the perfect crystals ideal for analysis. Second, these crystals are exposed to an X-ray beam from various angles, and the resulting diffraction patterns are recorded. In Franklin's time, these patterns were captured on photographic film, requiring precisely controlled exposures and careful development techniques. Third, the diffraction patterns must be analyzed mathematically through a process called Fourier analysis to convert the two-dimensional diffraction data into a three-dimensional molecular structure. Before computers, this calculation had to be done manually, an enormously time-consuming and error-prone process. Franklin's expertise in X-ray crystallography was exceptional. During her time in Paris, she had mastered advanced techniques for studying non-crystalline materials, skills that few scientists possessed. When she turned her attention to DNA, she brought not only this technical proficiency, but also an innovative approach to sample preparation and data analysis. One of Franklin's key innovations at King's College was developing methods to control the humidity of DNA samples. She discovered that DNA could exist in two forms, a dry A form and a wet B form with different structures. By carefully controlling moisture levels, she could obtain clearer diffraction patterns from each form separately, avoiding the confusing mixed patterns that had hampered earlier researchers. The famous Photo 51 that played such a crucial role in the DNA story represents the culmination of Franklin's technical skill. To obtain this exceptionally clear image, Franklin had refined her experimental setup over many months, adjusting the X-ray beam's focus, the exposure time, the sample preparation, and numerous other variables. The photograph shows a distinctive X-shaped pattern of spots arranged in a cross, a pattern characteristic of a helical molecule. The symmetry and spacing of these spots provided critical information about DNA's structure, including its helical nature and the spacing between nucleotide bases. What makes Franklin's achievement all the more remarkable is the primitive equipment available to her. At King's College, she worked with X-ray tubes that were temperamental and potentially dangerous in a small, poorly ventilated laboratory. The radiation exposure from these early X-ray machines likely contributed to the cancer that ultimately took her life. Without computer analysis tools, Franklin had to interpret her diffraction patterns through careful measurement, trigonometric calculations, and spatial reasoning. She constructed Patterson maps, mathematical representations of the X-ray data, by hand, a painstaking process that required exceptional precision and attention to detail. Franklin's training as a physical chemist, rather than as a biologist, gave her a different perspective on the DNA problem. She approached it as a structural question to be answered through rigorous experimental data, not through model building or theoretical speculation. This methodological difference partly explains the tension between her approach and that of Watson and Crick, who were more inclined toward model building based on available data. By early 1953, Franklin's analysis had determined several critical features of DNA: its helical structure, the location of phosphate groups on the outside of the helix, the presence of two strands running in opposite directions, and the specific dimensions of the helix. Had she continued this work uninterrupted, it seems likely she would have determined the complete structure independently. Understanding the technical challenges and methodological sophistication of X-ray crystallography helps us appreciate why Franklin's work was so crucial to unraveling DNA's structure. The technique required not just scientific knowledge, but artistic skill, mathematical ability, and exceptional patience, all qualities that Franklin possessed in abundance. The story of Rosalind Franklin extends beyond questions of individual recognition or historical correction. It illuminates broader issues about science as a human enterprise, how it works, who gets to participate, and how we remember scientific achievements. Franklin's experience demonstrates that science is not the purely objective, meritocratic process it is often portrayed to be. Scientific discoveries emerge from complex social environments where factors like gender, institutional power, and personal relationships influence whose work is valued and remembered. For young scientists, especially those from underrepresented groups, Franklin's story offers both caution and inspiration. It cautions that excellence alone does not guarantee recognition, that structural barriers can impede even the most brilliant careers. But it also inspires by showing that significant contributions can emerge despite these barriers, that scientific truth ultimately transcends the limitations of its social context. Franklin's approach to science also offers valuable lessons for contemporary research. Her insistence on solid experimental evidence before theoretical speculation, her technical rigor, and her willingness to question prevailing assumptions exemplify best practices in scientific methodology. In an era of replication crisis and methodological concerns across scientific disciplines, Franklin's example remains relevant. The delayed recognition of Franklin's contributions highlights the importance of how we document and teach scientific history. When textbooks and popular accounts present simplified narratives centered on a few celebrated figures, typically white men, they not only erase important contributors, but also present a distorted view of how science actually progresses. Scientific advancement rarely occurs through isolated moments of brilliance by lone geniuses. More often, it emerges through collaborative processes involving many minds, through incremental progress and shared insights, through technical innovations as well as theoretical breakthroughs. Franklin's story helps us see this more complex reality. Her experience also underscores the importance of scientific ethics regarding credit and collaboration. The use of her data without proper acknowledgement raises enduring questions about intellectual property in science, about the responsibilities of scientists to their colleagues, and about transparency in reporting discoveries. Perhaps most fundamentally, Franklin's story matters because it reminds us that diversity in scientific perspectives leads to stronger science. Franklin's background in physical chemistry brought crucial insights to biological questions. Her methodical approach complemented the more speculative styles of others working on the DNA problem. When certain voices and approaches are excluded from science, whether through explicit discrimination or subtle biases, the enterprise of knowledge creation itself is impoverished. In recent decades, efforts to recover Franklin's legacy have been part of a broader movement to create a more inclusive scientific community and a more accurate historical record. Organizations promoting women in science often invoke Franklin as both a role model and a cautionary tale, a brilliant scientist whose work changed our understanding of life itself, but who faced barriers that limited her recognition and potential impact. Programs like the Rosalind Franklin Society, the Rosalind Franklin Award for Women in Science, and educational initiatives highlighting her contributions seek not just to honor one scientist, but to transform scientific culture itself. These efforts recognize that correcting historical oversights is not merely about justice for individuals, but about creating conditions where future Rosalind Franklins can thrive and be recognized. The ongoing resonance of Franklin's story, the fact that we continue to discuss and reevaluate her contributions decades after her death, suggests that it touches something fundamental about science and society. It challenges us to consider whose contributions we value, whose work we remember, and what kind of scientific community we wish to create. In this sense, Franklin's legacy extends far beyond her specific discoveries. It encompasses the continuing effort to build a scientific enterprise that recognizes achievement regardless of gender, race, or background, a goal still not fully realized, but essential to both the integrity of science and the pursuit of human knowledge. The discovery of DNA's double helix structure in 1953 marked the beginning of a revolution in biology that continues to transform science and medicine today. Understanding DNA's structure revealed the physical basis for genetic inheritance and opened the door to manipulating the molecule itself. Developments that have led to genetic engineering, personalized medicine, forensic DNA analysis, gene therapy, and countless other applications. From the Human Genome Project's completion in 2003 to the CRISPR gene editing technologies of the 2010s, the DNA revolution has progressed at an astonishing pace. Today, entire genomes can be sequenced quickly and affordably, genetic diseases can be diagnosed prenatally, and the prospect of editing genetic material to cure inherited conditions is becoming a reality. This ongoing revolution all stems from that initial understanding of how DNA is structured, the discovery in which Rosalind Franklin played such a crucial role. The work of Watson, Crick, Wilkins, and Franklin revealed that DNA's double helix structure provided an elegant mechanism for genetic information storage and replication. The complementary base pairs, adenine with thymine, guanine with cytosine, along the two strands meant that each strand contained the information needed to reconstruct the other, a feature essential for DNA replication and genetic inheritance. Franklin's specific contributions to this discovery included 1. demonstrating conclusively through her X-ray diffraction work that DNA had a helical structure, establishing that the phosphate groups of the DNA molecule were located on the outside of the structure, determining that DNA existed in two forms, A and B, clarifying confusion in earlier research, calculating the precise dimensions of the helix, including the spacing between base pairs, producing the critical experimental evidence, especially photo 51, that enabled the building of the correct model. If we view scientific progress as a relay race rather than a competition with a single winner, Franklin carried the baton for a crucial leg of the journey. Her experimental work provided the empirical foundation upon which the theoretical model could be built. Without her data, the race to discover DNA's structure would have taken a different course, and likely a longer time. In the decades since the double helix discovery, our understanding of DNA has grown increasingly sophisticated. We now know about the complex machinery of DNA replication, the mechanisms of gene expression and regulation, the role of epigenetic modifications, and the vast portions of the genome once dismissed as junk DNA, but now recognized as having important regulatory functions. Each of these advances builds upon that fundamental insight into DNA's structure, an insight that required both theoretical creativity and solid experimental evidence. Franklin provided the latter, demonstrating the kind of meticulous, rigorous experimental work that grounds theoretical leaps in physical reality. As we marvel at modern genetic technologies, from DNA fingerprinting that has transformed criminal justice to genotherapies that treat once incurable diseases, we should remember that these applications rest on a foundation laid partly by Franklin's careful work with X-ray crystallography. The story of DNA's structure also illustrates how scientific discoveries often emerge from the combination of different approaches and perspectives. Watson and Crick's model-building approach complemented Franklin's experimental focus. Theoretical and experimental science are not competing methodologies, but complementary aspects of the scientific process. At its best, science integrates these approaches, recognizing the value of both theoretical insight and empirical evidence. Franklin's place in the DNA revolution reminds us that behind every scientific breakthrough lies numerous contributors, some celebrated, others overlooked. As we continue to build on the foundation laid in 1953, acknowledging the full range of contributions to that discovery provides a more accurate understanding of how scientific progress occurs and honors the diverse talents that drive it forward. Rosalind Franklin's life and work embody both the triumph and tragedy of scientific pursuit. The triumph lies in her extraordinary contributions, not just to our understanding of DNA, but to multiple scientific fields. Through meticulous experimentation and technical innovation, she helped unlock one of nature's most profound secrets, the structure that encodes life itself. The tragedy lies in how her contributions were initially marginalized, in the recognition that came too late, and in a promising scientific career cut short by illness. At just 37, with her most productive research years potentially ahead of her, Franklin's death represents not just a personal loss, but a loss to science itself. We can only imagine what further discoveries might have emerged from her laboratory had she lived a full life. Yet, in another sense, Franklin's legacy transcends both triumph and tragedy. As her true role in the DNA discovery has gradually been acknowledged, her story has become a powerful catalyst for change in how we think about science, gender, and recognition. Today, Rosalind Franklin serves as both a scientific role model and a symbol of resilience in the face of institutional barriers. Her name adorns research institutes, university buildings, academic prizes, and even a Mars rover, recognition that would have been unimaginable during her lifetime. Perhaps, most importantly, the recovery of Franklin's contributions has helped reshape our understanding of how science progresses. Rather than advancing through isolated moments of individual genius, science moves forward through the combined efforts of many minds, some theoretical, others experimental, some celebrated in their time, others recognized only in retrospect. Franklin's story reminds us that behind every scientific breakthrough lies a complex web of contributors, and that a complete history of science must acknowledge this fuller picture. It challenges us to examine which voices we amplify and which we silence, which contributions we celebrate and which we overlook. For students entering scientific fields today, Franklin offers both inspiration and caution. Inspiration through her intellectual brilliance, technical skill, and unwavering commitment to scientific truth. Caution through the recognition that excellence alone doesn't guarantee appropriate credit, that structural barriers remain to be overcome. As we continue to benefit from the DNA revolution that Franklin helped launch, as we sequence genomes, develop genetic therapies, and unlock the molecular basis of life, we would do well to remember her essential role in making these advances possible. Science and everyday life cannot and should not be separated, Franklin once wrote. Her own life embodied this principle, with her scientific work reflecting her broader commitment to truth and integrity. By recognizing her contributions more fully, we not only correct a historical oversight, but enrich our understanding of science as a human endeavor, one that progresses most effectively when it draws on diverse talents and perspectives. Rosalind Franklin never sought fame or public acclaim. Her focus remained always on the work itself, on the patient pursuit of scientific understanding. Perhaps the most fitting tribute to her legacy is not just acknowledging her role in one discovery, however significant, but recognizing the values she embodied: intellectual rigor, experimental precision, and an unwavering commitment to evidence-based conclusions. In recovering Franklin's place in scientific history, we do more than justice to one overlooked pioneer. We create a more accurate narrative of how one of science's greatest discoveries actually occurred, a narrative that can inspire future generations to pursue scientific truth wherever it leads, regardless of the barriers they may face. This has been Rosalind Franklin, Erased from DNA's Discovery. The second video in our 10-part YouTube podcast series, Forgotten Women Who Changed History. If you enjoyed this video, please like, subscribe, and share it with others who might appreciate this remarkable woman's story. Sources for this video include Rosalind Franklin, The Dark Lady of DNA, by Brenda Maddox; Rosalind Franklin and DNA, by Anne Sayre; The Double Helix, by James D. Watson; Archives of King's College London; The Rosalind Franklin Papers at the British Library; The Franklin Wilkins Collection at the Wellcome Library. Remember to check the description below for additional resources on Rosalind Franklin and other overlooked women in science and technology. Thank you for watching.